Good day. Welcome to the part 1 of 2 videos on chapter 1.4 about lines in space. So, we now have a model for space using algebraic vectors. But obviously we want to do more things. And one of the things that we would like to do is have more objects that we can play with. So a big question is, how can we define a straight line or just simply a line? Alright. Now, what is a line? We know a line would be a set of 3D vectors with some property. So if I have a line, I want to have a criteria whether the point is on the line or not on the line. Alright? Now, think about it. Say you have a line that contains point P and Q. Alright? Now, from this diagram, you can see point R is on this line, but S is not on this line. Alright? Now, what it has a property that R has that S doesn't have? Well, R has a property that it is between P and Q, and we will have a definition of what between means. So, S is not between P and Q, alright? So, being inspired by this simple diagram, it seems that we need a way to define algebraically, mathematically, what exactly do we mean by the concept of between in our model. Alright, so time for a mathematical definition. And here is the mathematical definition. Given distinct 3D vectors P and Q, we say 3D vector R is between P and Q if it satisfies a simple equation. If vector R is TP plus 1 minus T times Q, where T is between 0 and 1. Alright, now let's see why this is a good definition. Alright, so we are hoping that if we define things well, that if we look at this diagram, it looks like point R is between points P and Q and they all lie on the same line, that the norm of Q minus P, which is the distance from Q to P, is the distance from Q to R plus the distance from R to P. So if R is between P and Q, this equation must be true. Alright? But if the norm of Q minus P is less than the norm of Q to R plus the norm of R minus P, then it will not be between. Alright? So if we define things well, then this would be true, alright? And some good news, this is true, alright? And this is all captured in the first theorem of chapter 1.4. Here we go. So the theorem goes as follows. Let P, Q, and R be 3 distinct 3D vectors, alright? So P is not Q, Q is not R is not P, so 3 distinct vectors. It turns out that the norm of Q minus P is equal to the norm of Q minus R plus the norm of R minus P, if and only if, notice the word if and only if, R is between P and Q. Now to prove it, you will have to do 2 parts. You have to show that the first part implies the second part and the second part implies the first part. I'm not going to do it in this video, so that adventure I'm leaving for you to try, alright? But I'm going to give you an outline of the proof, alright? So please try the outline. So as I said, you have 2 jobs to do. So part 1, you assume that the equation is true and you want to deduce R is between P and Q. Now the definition comes in. What does it mean to be between? That means that R is of the form TP plus 1 minus TQ, where parameter T is between 0 and 1. So this is job 1 or part 1. Now to do this, you have to do a couple of steps. The first step is you've got to show that the norm of Q minus P squared is equal to the norm of Q minus R squared plus 2 times the norm of Q minus R times the norm of R minus P plus the norm of R minus P squared. So give it a go. Then you also have to show that the norm of Q minus P squared is equal to the norm of Q minus R squared plus 2 times the dot product of Q minus R with P minus R plus the norm of R minus P squared. Alright? So step 1 and step 2 you do independently. And then from those 2 results, you can deduce that Q minus R dotted with P minus R is equal to the norm of Q minus R times the norm of P minus R. So after doing step 1 and step 2, you get to deduce step 3. And now if you look at step 3 closely, you will notice that you actually have equality in the Cauchy-Schwarz inequality. All right? And we know when equality occurs, you've done the exercises in the textbook, that means there exists an alpha, a real number alpha, with a property that Q minus R is equal to alpha times R minus P. All right? Because you have equality in Cauchy-Schwarz inequality. All right? That's step 4. And in step 5, you need to deduce that alpha is positive. Why is that important? Because manipulating step 4, you can show that R is equal to alpha over 1 plus alpha times P plus 1 minus alpha over 1 plus alpha times Q. So R is a linear combination of P and Q. All right, that's just a little bit of algebra. All right, and then in step 7, I want you to show mathematically, all right, why is this alpha over 1 plus alpha, this expression between 0 and 1. So think about that, if you can do that. And thus, we have obtained that R is equal to TP plus 1 minus TQ, where T is alpha over 1 plus alpha. And this T is between 0 and 1. And so therefore, by definition, R is between vectors P and Q. All right, so that's only part 1. So for part 2, that is the converse, what you do is you assume that R is between P and Q, so you have a certain equation that is true, and then you have to deduce that the norm of Q minus P is equal to the norm of Q minus R plus the norm of R minus P. All right, so that's just a little algebraic exercise, so please give it a go. All right, and combining part 1 and part 2, you will have the proof. All right, guys, very important, also do the examples in the textbook. 1.4.3 is a good example to redo. Alrighty, so now we have the idea of betweenness, and now we can formally define what is a line. We say a line in 3 dimensions is a set of points. I want to underline, a line is a set of points of the following form. So a line is the set of points TP plus 1 minus TQ, where T is now any real number. Alright, so for this, P and Q are 3-dimensional vectors and P is not Q, so they are distinct. Right? Just some remarks on this definition. It is a set. Right? So a line is a subset of R3. If vector x is the element of L, then x is a point on line L, or x lies on line L. All right? That's just the language that we use. All right? If P and Q are sitting on line L, so L is referred as a line through points P and Q. Remember, P and Q are 2 different points. So L is a line through points P and Q. All right. If X is an element of line L, that happens if and only if X is of the form TP plus 1 minus TQ, where T is a real number. So this comes from set notation. All right. And the nice thing is you can actually expand this, and you can write this as 1 minus T times Q becomes Q minus TQ, where T is a real number. And then we can say this happens if and only if X is, we can take out a common factor of, so we have Q, and the terms with a T, it's T times P minus Q. All right? So all of this is known as vector equations. All right? So this is known as the vector equation of line L. All right? It's a vector equation because on the left hand side is a vector and the right hand side is a vector, and you have a parameter, and the parameter T is a real number. All right. Now, very important, the representation is not unique. I want to emphasize this. A line has more than one equation. So a single line can be described using infinitely many different equations. All right, so here's an example. So take a line L that passes through points P, Q, U, and V. All right, so if U and V are different vectors, we can also say the line is of the form TU plus 1 minus TV, where T is a real number. And so you can see how it is possible to produce infinitely many different equations for the same line. So do take note of this. All right, very important. Do not write down the line equals TP plus 1 minus TQ. Why is this bad? All right. Well, this is bad because the left-hand side is L, which is a subset of R3. The right-hand side is an element of R3, alright? So the left-hand side is a set and the right-hand side is a vector, and so you cannot use the equal symbol, alright? So please do not make this mistake in assignments and in tests and in exams, alright? The equal sign is a very special symbol. So what you have on the left, you must also have on the right. So if you have a set on the left, you must have a set on the right-hand side. Alright, now for a theorem. So let L be a line in 3 dimensions, so a straight line in 3 dimensions. And if P, Q, and R are 3 distinct points on line L, then exactly one of the following is true. That either P is between Q and R, or Q is between P and R, or R is between P and R. And we know this from our human intuition. If we look at a straight line given any 3 points, one point is always between the other 2 points, all right? But because of the way we define straight lines, because of the way we define betweenness, this is true, all right? The proof is in the textbook, and this theorem demonstrates that our definitions are doing great because it agrees with our human intuition, all right? Now, the next thing we want to define is the idea of a line segment. All right. So if you have 2 points, P and Q, so a line segment is all of the points, including P and Q, the endpoints, and all of the points in between P and Q. All right. So here's a formal definition. So consider distinct points P and Q as illustrated. There are 3D vectors. The line segment between P and Q is a set of points S equals, it's a set. So it's a 3D vectors of the form TP plus 1 minus TQ, where T is between 0 and 1 inclusive. All right. So you can see, for example, if T is 0, we get 0 times P plus 1 times Q, which is Q. So T equals 1 gives us vector Q. If T is equal to 1, then we get up 1 times P plus 0 times Q, which is vector P. So when we use parameter T is equal to 0, we get vector P. When we use parameter T is equal to 1, we get vector Q. And if we use, let's say, T is equal to a half, we get the point that is in between the midpoint of this line segment. And likewise, if we have T is between 0 and 1, we get any other point on that line segment. All right. So look closely at the definition. I want to emphasize T can be 0, T can be 1, or T is between 0 and 1 inclusive. All right. We can also define another idea, a sun ray or a ray. All right. So you have, it starts at point Q, and you want to have all of the points radiating outwards containing point P. So here's the definition. So consider distinct points P and Q in R3. A ray is a set of points of the following form. So R is TP plus 1 minus TQ. And notice the condition. T is greater or equal to 0. We can also rewrite this as all of the points of the form Q plus T times P minus Q, where T is greater or equal to 0. And you can see it works because if you plug in T is equal to 0, you get point Q. If you plug in T is equal to 1, you get point P. And just for fun, let's plug in 2. If we plug in 2, we get Q plus 2 times P minus Q, which works out to be this point, 2P minus Q. All right, so this would be a ray. All right, so there's a nice table in the textbook where they look at how the definition varies of a line, a ray, a line segment, or between. All right, so it all boils down onto the conditions of the parameter. All right, but again, I want to emphasize, please make your own summaries. All right, so that you synthesize the information and make sure that you're comfortable with, you know what a line is, you know what a ray is, you know what a line segment is, you know what the word between means, because these are the words you will be seeing. All right, these are the words that we assume that you know. All right. It's very important to redo the textbook examples and the exercises, or even make your own examples, all right? So you can pick any 3D vectors A, B, P, and Q, and you can ask, is the point A on the line that passes through P and Q? Or is point B on the line segment between P and Q, all right? So if it's on the line, ultimately you want to show that the parameter t is a real number. If it's on the line segment, you've got to show that your parameter is between 0 and 1, all right? So knowing your definitions will guide you on how to solve the problems, all right? Now, a more interesting question would be, let's say we have two lines. Do two lines always intersect or not? And given two lines, what possibilities can occur for the intersection? All right, so this is something we're going to explore next. All right, but before we explore it, let's look at an example. Let's take the following example. Let line 1 be the line through point P and Q, and let line 2 be the line through point A and B, and those are the 3D vectors given. This is the question. Determine whether or not line 1 and line 2 intersect. If they do intersect, find all the points of intersection. All right. Now, this is a multi-step problem. So you've got to make sure that you provide a well-written answer. All right. It might help drawing a little diagram saying, so for example, here you have line 1. It passes through P and Q. And then you have line 2 that passes through A and B. And you're hoping to find a point sitting on both of the lines. All right. But it's good to already start practicing writing out good solutions. All right. So let's start off by investigating each line. So let's start off with line 1. So line 1, and we're going to look at the vector equation. So we know that the vector equation is x is equal to TP plus 1 minus TQ, where T is a real number. So tell yourself what T is. T is a real number. Now we're given that P is the vector 1, 0, 1. And Q is the vector 0, 2, 0. So multiplying this vector with a scalar becomes a vector. That vector with a scalar becomes a vector. And if you simplify it, it becomes the vector t, 2 minus 2t, t, where t is a real number. All right. So now we have a vector equation for line 1. All right. So now we continue. Now we look at line 2. Now line 2 is a different line. All right, this is a different line, and so we got to use a different parameter. All right, so one of the traps is to use the same parameter, and if you use the same parameter, sometimes your answers will be completely wrong. All right, and you will not even get any marks. All right, so if you have two lines, you've got to use two parameters. If you have three lines, you've got to use three parameters. So here I'm going to say the line is of the form x is, remember it passes through points A and B, so you can see why the diagram helps. It's SA plus 1 minus SB, where S is a real number. All right. And now we're given that S is the vector 2, 1, 2, and we're given that B is the vector 0, 3, 0. So if we do the mathematics, I'm going to leave it for you to check. This becomes 2s, 3 minus 2s, 2s, where s is a real number. All right. So already, paragraph 1, you look at line 1. Paragraph 2, you look at line 2. All right. And you can also see, it's easy for you to read, and it's easy for the marker to see what are you doing, how are you going to solve the question. And now we're going to have another paragraph. Let's call it intersect. All right. Now, at the moment, we do not know if the lines do intersect or not intersect. All right. So let's start this paragraph off by saying, if x is a point sitting on both line 1 and line 2, so it's sitting in the intersection, then x is the element of line 1 and x is the element of line 2. All right. So thus, x is equal to t 2 minus 2t, where t is a real number. Why? Because x is sitting on line 1. And x is of the form 2s, 3 minus 2s, 2s, where s is a real number. Why? Because x is also sitting on line 2. All right. Guys, we want to see, marks will be allocated for us to see that if a point is sitting on both lines, the point is sitting on line 1 and line 2. Yes, it is obvious, but you got to state this. All right. We got to be able to understand how you go about solving this. So therefore, we have that this vector t, 2 minus 2tt, is equal to this vector 2s, 3 minus 2s, 2s. And so we know from the very first video that two vectors are equal if all of the components are equal. So we know that t is got to equal to 2s. Let's call that equation 1. 2 minus 2t is got to equal to 3 minus 2s. That's equation 2. And you also got to look at the last component. T is equal to 2s. That's equation 3. All right? And so we are looking for real numbers t and s that makes all of that true. All right? Now we see 1 and 3 is same. So only need 1 and 2 to be true. So we only need that t is got to equal to 2s and 2 minus 2t is got to equal to 3 minus 2s. All right? Let's maybe call it 4 and 5. All right? And now if we add 4 and 5, I'm needing more space. So if we add 4 and 5, then we get that something beautiful happens. So you've got two equations, two unknowns. There are many ways of solving it. I'm going to add it. So if we add 4 and 5, we get 2 minus 2t plus t becomes 2 minus t. 2s plus 3 minus 2s becomes 3. And so if we solve it, so from 6, we see that t is equal to minus 1 sub into 4, we get s is equal to minus a half. All right? Now, we got to make sure that we get a point that is sitting on both lines. All right? So now, t equal to minus 1. So unique solution. So first, let's make a note of that. So unique solution. All right? So t equal to minus 1 gives, remember, it's t, 2 minus 2t, t, and this becomes, when t is minus 1, becomes minus 1 for minus 1, which is sitting on line 1, because it's of the form t, 2 minus 2t, t. All right? And now s is equal to minus a half gives that, remember, to be sitting on line 2, it's got to be of the form 2s, 1 minus 2s, 2s. So if you plug in minus a half, this works out to be minus 1 for minus 1, which is sitting on line 2. And so, line 1 and line 2 intersect. They intersect in a single point, the point minus 1 for minus 1. So, this is an example. We have two lines in space intersecting in a singleton, a unique point, minus 1 for minus 1. All right? So we're looking for well-written answers, all right? So we've solved the system. We've got a unique solution. And so we get there's only one point sitting on both lines. Again, I want to emphasize, remark, two lines means two parameters, all right? Here, I use s and t. All right? There are more examples like this in the textbook. Examples plus exercises like this. Do them. All right? Practice makes perfect. All right? And so we see that one possibility, given two lines of the intersection, is a single point. But are there more possibilities? All right? And I'm going to finish this video by asking you to think about, given two lines and the intersection of two lines, what other possibilities can occur? I hope you've enjoyed this video. Please tune in for the second video on chapter 1.4. Have a good day. Bye.